we are looking at proofs. So earlier we had seen proofs with using deductive reasoning, correct? So we started with a statement which was true and then we would deduce the other results. We will look at other methods of proving as well, and in this we will be using some examples. The first example is prove that n cube minus n is a multiple of 6. That means it's divisible by 6, correct? So let's look at n cube minus n. I'll be rewriting it as take n common, n square minus 1, and factorize n square minus 1 further into n plus 1 into n minus 1. If you look carefully at this, and I'll rewrite it so for you to see it clearly, n minus n 1 times n plus 1. Do you notice that this is like a product of 3 consecutive numbers? And in that case, definitely one of them will be an even number, a multiple of 2, and the next for a multiple of 3. So therefore one of them, out of the 3, one of them will definitely be a multiple of 3. One of them is a multiple of 2, so surely it must be a multiple of 6. So just by factorizing and rewriting it, I could prove that n cube minus n is a multiple of 6. This is a proof, of course, again a deductive proof, because I used my knowledge that product of 3 consecutive numbers is divisible by 6 and to prove this, correct? The next question says to use method of contradiction. This is what we are doing, and the question says a is divided by 3, and whenever a number is divided by 3, it either leaves a remainder of 0, 1 or 2. Once it crosses that, then the next number is again divisible by 3, correct? So a is one of them. It's either 3n, which means it's a multiple of 3, or it is 1 more than a multiple of 3, or it's 2 more than a multiple of 3. Prove that if a is a multiple of 3, then a square is also a multiple of 3. So they are not really telling us a method there. And then prove by contradiction the converse of the treatment, that the statement that if a square is a multiple of 3, then a must be a multiple of 3. Okay, so let's see that if a is a multiple of 3, which means a must be a 3n. So a square will be 9n square, which means 3 times 3n square. So therefore a square will definitely be a multiple of 3, correct? Prove by contradiction that the converse is true. If a square is a multiple of 3, so okay, if a square is a multiple of 3, then, and if a is not a multiple of 3, so an a is either of the form 3n plus 1 or it is of the form 3n plus 2, correct? So this is a multiple of 3. Then what will a square be? If a is not a multiple of 3, then it either will be a square of this, which means if I use my knowledge of a plus b the whole square, it's 9n square plus 2ab, which is 6n plus 1. And this is not a multiple of 3. You can very well see that I cannot take 3 common out of this. Similarly, if I take a 3n plus 2 the whole square, I know it's 9n square plus 12n plus 4. Again, this one is not a multiple of 3. So whenever I'm assuming that a is not a multiple of 3, then a square is also not coming. So by contradiction, so if I'm assuming that a is not a multiple of 3, then I'm contradicting the result that a square is a multiple of 3, and therefore I will, by contradiction, I can prove that if a square is a multiple of 3, a must be. So in contradiction, all I do is I look for an opportunity to contradict what is already told to be true, and if that is happening, then I have. Next is, if root 2 is an irrational number, then root 2 plus 1 must also be irrational. Okay, so again I'll try to use contradiction. So root 2 is irrational, so it cannot be expressed in the form of a plus b, where a and b are integers and b is not 0, correct? However, I am saying that root 2 plus 1 The question says that if root 2 is irrational, root 2 plus 1 is also irrational. But I am saying that root 2 plus 1 is rational. So I am trying to assume this is true. If that is the case, if it is rational, then it must be expressed in the form of a by b. And therefore root 2 is a by b minus 1, which is a minus b upon b. If a and b are both integers, then a minus b upon b is also an integer upon b. But this contradicts the result that root 2 is an irrational number. Then how can root 2 be expressed as a ratio of two integers? So therefore my assumption that root 2 plus 1 is a rational number must be wrong, because that led me to this result. So therefore by contradiction I can prove that if root 2 is irrational, then root 2 plus 1 is also irrational. Again the question says use contradiction to say that there exists no integers a and b where 6a plus 2b is 35 and 6a plus 9b is 35. No such integers can exist, and by contradiction. So I am assuming that 6a plus 2b is equal to 35 has integer solutions. So if that is true, look at the left hand side. If I take 2 common, I can rewrite it as a even number. So my left hand side is an even number, but 35 is not an even number. If there is an integer solution, this cannot be possible. So it's contradicting the fact that left hand side is an even number and right hand side is an odd number, and therefore my assumption that this has integer solution is incorrect. Same way, 6a plus 9b is 35. I can take 3 common on the left hand side and this becomes 2a plus 3b. So my left hand side becomes a multiple of 3, but my right hand side is not. And that is not possible if a and b are integers. Therefore again a contradictory result. Another example can also be by counter example. So all I have to do is look for a value where it's an opposite example which doesn't satisfy the rule. That can also be a method of proving, and we'll look for an example there. So the next one says 2x raised to 5 minus 6x square plus 14x is equal to 1 has no integer solution, and we have to prove by contradiction, so we will assume that it has an integer solution. So if we look at 2x raised to 5 minus 6x square plus 14x, the left hand side all are even numbers, correct? Multiples of 2. So if x is an integer, then the left hand side is an even number, but 1 is not. So that itself is telling you that that's not possible. Same way here, if it has an integer solution, then this is what it will result in. So left hand side is a multiple of 3 and right hand side is not. If x was an integer value, then it cannot be possible that left hand side is a multiple and right hand side is not. Therefore again we are contradicting the result, which is why it's not true. So you must have understood by now that the idea of contradiction is to prove that the existing rule is getting contradicted. Prove the following statements. If n is odd integer, then n square plus 2n plus 5 is even. Let's take any odd integer. So if it's n is an odd integer, then n can be written in general form as 2m plus 1. So n square plus 2n plus 5. Let's expand this. So I get 4m square plus 4m plus 1 plus 4m plus 2 plus 5. So 4m square plus 8m plus 8. I can take 2 common and I get 2m square plus 4m plus 4, which means it's an even number. So by assuming n as odd, a general odd number, I could prove that n square plus 2n plus 5 is even. And if n square plus 2n plus 5 is odd, then n is even. So the other way around, if that is odd, then n is even. So let me assume that n is odd. And I know already from my part A that if n is odd, then this number has to become even. But if this is odd, then n has to be even. There is no doubt about it. Or let me start the other way around, that I'll take n as an even number and substitute in that and give you the result that it is. So if n is an even number, then it can be expressed as 2k. So 2k square plus 2 times 2k plus 5. So 4k square plus 4k plus 5. So I can rewrite this as 2 times 2k square plus 2k plus 2 plus 1. So this is the format of an odd number. So by starting with an even number, I reached to a result which is an odd number. So therefore, but I could also prove it by contradiction because part A is giving me the answer to it, correct? So these are few examples where you can use proofs in a different format other than deduction. And like I said, counter